level languages, which is one of the great contributions of computer science. And the second problem with the Turing machine is the memory model. It's a single tape of cells, which is okay, but the access is only at a single point. You have a read-write head that can only move one step at a time in any direction. And if you actually want to do, for example, addition, as Avi was talking about this morning on a Turing machine, you can't really add two numbers in linear time unless they're written on the same part of the tape and your head starts at one position and can read the two inputs simultaneously. If the inputs are separate, you have to run back and forth between the two inputs to do the addition, and addition looks more like quadratic time than linear time. So if one actually wants to do programming, the right kind of model is not a Turing machine, but something more like a random access machine where the memory consists of an array and you get constant time access into the various positions. I'm going to talk about some data structure results, about search trees and balanced search trees, which is one of the most basic and ubiquitous data structures in computing. And not only is it the 100th anniversary of Alan Turing's birth, but it's essentially the 50th anniversary of the discovery of the first kind of balanced search tree, the AVL tree. Before I get into the details here, let me just make a few additional comments about computer science. Unlike mathematics, physics, chemistry, it's still a very young field. And we as researchers look for the low-hanging fruit often. We settle for the first solution as long as it's good enough. But this first solution may not be the best possible solution. The design space, design of algorithms, is incredibly rich. And with Moore's law, it only becomes richer and richer. As Dijkstra was fond of pointing out, the number of levels of hierarchy that we can build up is enormous, and computer science is kind of unique in this way because computers are so fast, they operate so much faster than human time. So here's another observation. What people do in practice can be surprisingly simple because, again, programmers pressed for time choose the first solution that works for them, and they don't bother to think about perhaps there's a better way. So first of all, theory should say something not only about beautiful, elegant, best possible algorithms, but it should also say something about the methods that people actually use in practice, why they work or don't work. And we should try to provide, as theoreticians, simple methods, methods that can actually be used in practice. At least this is my point of view. So my research agenda, and I'm an algorithms designer and analyzer primarily, is to extract simplicity. For fundamental problems, try to systematically explore the design space to find the best solutions. I love this word, it's overused, but nevertheless, here's a nice definition. Seeking elegance, a quality of neatness and ingenious simplicity in the solution of a problem, especially in science or mathematics. And in particular, we want to keep the algorithm design simple so that a programmer can actually write the short code that will allow the thing to run in practice. But the underlying theory that supports the algorithm can be arbitrarily complicated, and that's where things get interesting in many ways. So we want to study methods that are used or can be used in practice. This is a quote from Einstein, or a paraphrase of a quote. Try to make everything as simple as possible, but not simpler. All right, so this brings me to the story behind this work. Now, as I mentioned, balanced trees are a 50-year-old data structure. It's a solution to an indexing or a search problem, as I'll describe in some detail. We want to maintain a collection of items that we can search in, but the set is going to be dynamic. We want to be able to do insertions and deletions and maintain efficient access. Once upon a time, there was an online e-commerce provider that decided to build an online customer database for their customer information. They contracted with a database provider to build them a database. Now, the standard solution would be some kind of B tree, but for one reason or another, perhaps they wanted to fit the whole thing into main memory of the computer, they decided to build a binary search tree to support the database. They took a standard solution from the computer science literature, the red-black tree, but they built a brain-dead version of this data structure. They did rebalancing on insertion, but not on deletion, and we'll see what this means going forward. So even though the theory, if they had done it correctly, would say that the search time should always be roughly logarithmic in the number of elements, in fact, their data structure did not have this property. Furthermore, they compounded this difficulty by building into their code a maximum height on the tree depth. Their height was 80. In a red-black tree properly built, you should be able to store 2 to the 40th items in a search tree of height 80, and 2 to the 40th is a big number, big enough for all practical purposes. If the height bound was exceeded, the hypothesis was something was wrong. They would then bring down the entire system and rebuild the database. Okay, but they thought this would never happen, and if it did happen, it would happen in debugging, and it would reveal some fundamental flaw in their implementation. They installed their database. It ran fine for a while, but then all of a sudden this height-bound test was triggered. The whole system came down, tried to rebuild itself, triggered again. The whole system was down for several days, ended up in a lawsuit. The question is, from a theoretical point of view, what went wrong? How can we fix this? So that's the story. So in order to understand this question, we have to understand search trees a little bit. So let me now talk about the problem and the class of data structures and get into some of the details. All right, so the searching problem is fundamental. We want to store a collection of items, each with some key, such as names and phone numbers. You want to look up a phone number, you go to the phone book. You can page through one page at a time, or you can do something faster. You can open the phone book halfway, see if you need to go to the first half or the second half. First half or the second half for you. Okay, the operations we want to do are access a given item based upon its key and return the associated information. Insert a new item into the dictionary along with its associated information. And delete an item currently in the dictionary and remove its associated information. We want all these operations to be efficient. The simplest way to solve this problem, and the way you would do it on a Turing machine tape, is just store the items on the tape, but then you have to go through all the items in the worst case in sequential order to find the item you're interested in, and on average you have to go halfway through the list. This is very expensive. We can also solve this problem using a hash table, if you know what this is, which gives us constant access time, and this is an example of a randomized algorithm. The trouble with the hash table, which sprinkles items arbitrarily into memory in a mixed up order, that's why it's called a hash table, is that it loses information about the order of the items. So our assumption is going to be, first of all, that the items or the keys on which we're doing the searching are totally ordered, such as names in alphabetical order or numbers in numeric order. This means that binary search is possible. And we're going to build a data structure, a search tree, a binary search tree, which takes advantage of that fact. And it has some additional properties. In particular, since the items are in sequential order, if we want to do a range query, if we want to find all items between a given lower bound and a given upper bound, we can report them fast. This is not possible to do in a hash tree. All right, so a binary search tree is a data structure that is a concrete implementation of this idea of opening the phone book halfway, deciding whether you should look in the first half or the second half, and applying that idea recursively. If you're looking in the first half, look at the first quarter position and see if you should be in the first quarter or the second quarter, and so on. All right, here's a binary search tree. The items I'm storing are just the letters. The order is alphabetical. In truth, the keys would be something more complicated, and each item would have some additional information stored with it, which I'm not illustrating here, okay? To find an item, say the letter P, we compare P to F. We start at the root of the tree. Every node in this tree has two children, a left child and a right child. The children may be missing. Node X only has one actual child. Node F has two. Node P has none. A node with no children is called a leaf. And a node with one child is called a unary node, and all the others are binary. So I want to find P. I start at the root, which is the top node in the tree. And notice we as computer scientists draw our trees upside down, which is a historical artifact. But we're searching from the top down, from the root to the leaves. We compare it to F. P is greater than F. We take the right branch. We compare it to M. It's greater. We take the right branch. Compare to X. It's less. We take the left branch. We find it. If we don't find it, we run off the bottom of the tree. We know the item is not in the tree. Insertion is not much harder than a search. We search for the item we're interested in this case R, which is not in the tree. The search path goes by P to the right-hand missing node. We can just drop R into that position, create a new node containing item R. Now, what's the advantage of this kind of data structure over just listing the items in order and searching from the front? Every time we take a step down, the hope is that we're splitting the number of items we have to look at the next step roughly by a factor of 2, so that the number of steps down is only logarithmic in the number of items, which becomes important if we're storing 1 million, 1 billion, 1 trillion items. And this kind of data structure becomes only more important as the collections of data that we're doing computation on grow, which is what they're doing. Okay, so far all is straightforward. Now, what if we want to do a deletion? Deletion is a little bit more complicated. If I want to delete a leaf, I can just find an item in a leaf. I just find where it is in the tree. If I wanted to delete R, I can just remove it. If I want to delete a unary node, one with only one child, such as X, I can remove it and replace it by its only child, P. Let's see, an important point that I didn't make here is that the items are stored in this tree in symmetric order. That's left to right order, which means that for any node, everything in its left subtree is smaller than it is, and everything in the right subtree is bigger than it is. That enables us to do this binary search process. Okay, so I can easily delete X, and then P would become the right child of M. Everything in the right subtree of M is bigger than M. But if I want to delete F, for example, I have a problem. Well, it's a root. I can't make both D and M a root. Or if I wanted to delete D, I have a similar problem. I can't make both B and E the left child of F. So deletion becomes more complicated than insertion. This is the first place where we see that deletion is more complicated than insertion. The general idea is we want to find the item to be deleted, which we do by the search process. Remove the node and repair the tree. As I mentioned, this is easy if the item is stored in a leaf, a node with no children, or if it's stored in a unary node. But if it's stored in a binary node, we have to do a reduction. We'll find a unary node in which we can stick it, and then we'll delete a unary node or a leaf in which we can stick it, and then we'll do the deletion. So the standard way to do this is by swapping. For example, if we want to delete node P in this item M in this tree, yes, M, we want to delete M. Now M is binary, so we can't make both G and X the right children of F. Instead, we find the successor of M, which we get by taking the right branch and then taking left branches all the way to the bottom until we would run off the bottom of the tree. That takes us to node P, item P, which is the immediate successor of M. We swap M and P, so P is now in the binary node, M is in the unary node. We can now delete the new node containing M and reattach Q as the left child of R, and we're done. So by this swapping, we reduce the binary node deletion case to either leaf deletion or a unary node deletion. And that's the outcome of this deletion process. Now, the best case for this data structure is when everything is packed as closely to the top as possible. That is, that the tree is completely filled level by level until possibly there's one partially filled level. Then the maximum path length in the tree is binary logarithm of the number of items in the tree. Number of items n, binary logarithm, roughly +1 actually. Okay, so instead of searching linearly, we reduced the search time and also the insertion and deletion time to traversing a single path in this tree, which is logarithmic. Now this is exponential speed up. This is just like taking an NP-complete problem and going from an exponential time search to a polynomial solution, reduced to efficient algorithms. But this is the same huge impact. Logarithmic is a whole lot better than linear, or even slightly sublinear. And as n increases, if we're dealing with millions or billions or trillions of items, this becomes important. Now, if we're presented with the entire set of items ahead of time, we can easily build a perfect tree like this. But not if we're doing insertions and deletions, because we have to restructure lots of the tree to maintain this property. So the goal now is to maintain constant logarithmic depth in the presence of insertions and deletions, and to come up with ways to rebalance the tree as we do insertions and deletions. All right, now there's been a lot of work on average case analysis of this data structure. It turns out that if you insert items in random order, completely uniformly random order, you will get a tree that has constant log n depth. That's the expected depth. So if you're willing to live with the average case, maybe things are okay. But there are natural insertion orders that are very bad. In fact, the most natural insertion order is very bad if you don't do rebalancing. That would be just inserting items in sequential order, alphabetical order. If we did that, we would get this tree, and now the average search time and the worst case search time is linear instead of logarithmic. We've given up our exponential speed up. And this is not only an example, this happens all the time. So in spite of the fact that unbalanced trees with random insertion order in the average case are good, this is not a data structure to use in practice because there are natural bad instances. Okay, so our goal again is to modify the tree as we go along, as we do insertions and deletions, to keep the depth logarithmic and in ways that don't require too much rebalancing. So the first question is how to define the balance of the tree, and also how to restore the balance after an insertion or a deletion. All right. The standard restructuring primitive for these binary search trees is called a rotation. It's an operation that is local to the tree structure. It moves certain nodes up and moves other nodes down. It takes constant time, and it can be used to improve the balance of the tree. And by doing enough rotations, you can convert any tree on a set of items to any other tree on the same set of items. And it preserves the symmetric order, so it preserves the searchability. And here's what it looks like. If I have a node Y with a left child X, and the three subtrees of the two nodes are the ABC subtrees, and Y can be sitting arbitrarily in the middle of a tree, Rotating at x makes x the parent of y. Y becomes a right child of x. The A, B, and C subtrees are attached in left to right order to maintain the searchability property. This moves the A subtree up, moves the C subtree down. The B subtree is reattached, but its depth remains the same. So if there were long paths in the B part, in the A part, I could reduce their length at the cost of increasing the length of paths in the C part. Now we want to do rotations in the presence of as we do insertions and deletions so as to preserve logarithmic depth in the tree. Now there's also this question of how to define balance. And now let me summarize what I'm going to try to say in this talk. First of all, there's a general way to define balance, height-based balance in binary search trees, which I'll call ranked binary trees, which provides a general framework for looking at different classes of balanced trees and rebalancing algorithms. There's a natural generalization of AVL trees, which I'll call rank balanced trees, which have very nice properties in this large class of balanced tree structures. By using appropriate analytic techniques, namely exponential potential functions, we can prove interesting things about some of these tree structures. In particular, we can prove that not only can you do rebalancing efficiently, that is in logarithmic time, but most of the rebalancing action happens at the bottom of the tree. Now these data structures, big databases, we don't want to do single accesses. We want to have multi-threaded potentiality. We want to allow multiple searches and possibly multiple updates going on at the same time. And if the action is at the bottom of the tree, then it's easy to have multi-threading going on. But if all the action is happening at the root, then that becomes a bottleneck. And since every search has to go through the root. And getting back to my story, we can in fact avoid doing any rebalancing on deletion if we do it properly. And in fact, the theory tells us, gives us hints as to what to do, how to do it correctly, and how we would do it wrong. All right, so now we're interested in the maximum path length, which is the worst case search cost in the tree, the number of nodes from the root all the way down to a leaf. Now, Adelson, Velsky, and Landis, who were two Russians who developed the original balanced tree data structure in 1962, wrote a 4-page paper on this in which they talked about, they defined search trees, they looked at rotations, they defined their balance condition, and they described how to do rebalancing on insertion. Their balance condition was to say that for each node, the maximum path length down the right side, down the left side, and the maximum path length down the right side were within one of each other. I'm going to generalize that idea. Instead of keeping track of the height, I'm going to give each node a rank, which is going to be an integer, which is a proxy for the height, within a constant factor of the height, depending upon exactly the further structure I impose. So and the height is going to, the rank is going to generally go up as we go up in the tree structure. And we're going to give leaves rank 0 just as a convention and missing nodes rank -1. If we go back and look at that picture of essentially the perfect tree, the really perfect tree would have all the leaves at rank 0, all the next nodes at rank 1, rank 2, rank 3, and so on. The rank would be exactly equal to the height. That's the best case. So what's important here is the difference in rank between a node and its parent. And to capture that, I'm going to do it in two different ways, looking up and looking down. So the rank difference of a node that is not the root is just the difference between its rank and its parent's rank. 1 is the perfect case. These are generally going to be positive, but not necessarily. Given this definition, I'll say a node is an I child if its rank difference is I. So it's a 1 child if its rank is 1 less than that of its parent. A 0 child if it has the same rank as its parent. A 2 child if it has rank difference 2 from its parent, and so on. That's looking upwards. And looking downward, if I have a node and I look at its two children, I'll say it's an IJ node if its two children have rank differences I and J. And I'm not going to distinguish between left and right in this talk because essentially everything I'm going to say, there's a left-right symmetry, although there are some situations in which you might want to allow non-symmetric structure in your tree. Okay, so the ideal case would be all rank differences 1, which we know we cannot achieve if we're going to require that all the leaves have rank 0. The AVL trees of Adelson-Velsky and Landis, as I said, described in a 4-page paper in 1962. In this framework, the balance condition is that all nodes are 1, 1, or 1, 2. That is, if you look at every node, its two children both have rank differences 1 less than it does, or else one of them is rank difference 1 less and the other one is rank difference 2 less, and I don't care about left and right here. Turns out that with this requirement, the height is exactly equal to the rank, and you can prove that the height is logarithmic in the number of nodes. And the constant factor is 1.4404, which is log of the golden ratio, binary log of the golden ratio. The golden ratio being 1 plus square root of 5 over 2. There are amazing instances in computer science where classical ideas come in, and this is one of them. The golden ratio goes back at least to the Greeks, if not before, and it's the solution to a simple quadratic equation which comes out of the analysis of these data structures. Okay, so here's an example of an AVL tree, and I apologize for the number of numbers in here. The blue numbers are the ranks. So the leaves all have rank 0. Numbers on the left are the ranks. The missing nodes off the bottom all have rank -1. The black numbers are the rank differences, either 1 or 2. These are the values I store to define the balance in my tree. I only need 1 bit per node indicating whether its rank difference with respect to its parent is 1 or 2. The original definition of AVL tree, you actually need a 3-way state per node because this definition, in fact, pushes the balance information down by a node, which gives us a little bit more efficient balance information storage. All right, so that's the data structure in its static form. We've now got, if we can maintain the balance when we do insertions and deletions, then we're guaranteed logarithmic time for searches and for insertions and for deletions. So how do we do rebalancing? Before I do that, I want to look at another well-known kind of search tree that fits into this framework, and that's the red-black trees, which were actually invented by Bayer in 1972 with a different name, but there's a beautiful paper called The Dichromatic Framework for Balanced Trees by Gibas and Sedgwick, in which they put 1 bit of balance information on each node and called the node either black or red, depending upon the value of the bit. We can embed their trees in our framework, and what happens is that the rank differences are either 1 or 0. Okay, so we can have 2 nodes in a row that have the same rank, but there's an additional constraint, which is that we cannot have 3 nodes in a row that have the same rank. That is, a 0 child has a parent that's a 1 child. Mapping to their framework, the 0 children are the red nodes and the other nodes are the black nodes. You can't have 2 red nodes in a row. Now the relationship between the height and the rank is a little weaker. It's within a factor of 2, and we're guaranteed that the maximum path length is at most twice the binary log, which I didn't put in here. Okay. But given this general framework, we can actually consider alternative definitions of balance. I mean, here we have rank differences 0 and 1. If we go back to the AVL tree definition, we allowed, where did we go here? We allowed 1, 1, and 1, 2, but it's natural to allow arbitrary rank difference 1 and 2. That would give us a generalization of AVL trees. And that's what we call rank balance trees. All the rank differences are 1 or 2, and we need one extra constraint to make this an especially nice data structure. We require, well, it's automatic from the way I've set up the definition. The leaves are at rank 0, so they're all 1, 1. All right. Now, this is very similar to red-black trees. Now the height is somewhere between the rank and half the rank. And I'll come to this even more general data structure that fits into this framework later on, the so-called ravel trees or relaxed AVL trees, where we basically throw out all strong constraints on the rank differences except that we require them all to be positive. There are many other kinds of balanced trees. The ones that define balance somehow related to height fit into this framework. There are others where the balance depends upon the subtree sizes, like weight balance trees, that don't fit so nicely into this framework. Okay. Now, with all these kinds of balanced search trees, the rebalancing on either insertion or deletion proceeds either bottom up or top down. If we're rebalancing bottom up, we do an insertion. If we violate the balance condition, we have to fix things up, doing rotations and changing ranks or changing balance information, walking back up the tree. Same thing in deletion. With some of these, but not all of these different kinds of balanced tree structures, we can do the rebalancing proactively top down, which is nice if we're in a concurrent environment because we know how, if we do rebalancing top down, we don't have to block things up above to worry about rebalancing bubbling up later on. All right. Now, it turns out that AVL trees have a very nice property, which is that not only can you do the rebalancing by doing rotations just along the access path, but it only takes 2 of them, at most 2 rotations. And the process involves doing the insertion, walking back up the access path, changing some ranks, doing promotions, increasing the ranks of certain nodes by 1, until everything gets fixed up, or there is a situation in which you can repair the tree by doing 1 or 2 rotations and changing some ranks. Okay, and let me just illustrate the cases here. I'll try to avoid the technicalities as much as possible, especially since if I don't, I'm going to run out of time here. But there are essentially 3 cases and times 2 because there are mirror image cases. And one complaint about balanced search tree schemes is the number of cases. Essentially all balanced binary tree schemes that I know of, there are 3 cases and possibly 6 cases if you have to worry about mirror image, and they all look like this and they're combined in different ways. There's one case where you have to change the balance information but not restructure the tree. That's the top case. There's a promotion. There's one node there that has its rank increased by 1, and that can propagate. Then there are 2 more cases. There's a single rotation case, which is the top branch here, and a double rotation case, which is the bottom branch here. And with AVL trees, if you ever have to do the single rotation case or the double rotation case, that's the end. So in AVL trees, again, the general way the insertion process works is you walk down the tree, insert the new item, it gets a rank of 0. Its parent might have a rank of 0, in which case there's a rank difference of 0, which is a violation. And then we have to go through the appropriate bottom-up rebalancing, just applying the appropriate case until the thing is fixed. But only 2 rotations maximum, so there's not a lot of restructuring. And here's a very fast example. We insert A at the bottom, and these are rank differences now. So A has rank 0, B has rank 0, A has rank difference 0, that's bad. The first thing that happens is a promotion of B, and now it has rank difference 0, and then we do a single rotation. And here's an insertion of D, which ends up doing a double rotation several steps up the tree, and we end up with this tree, and so on. Now, deletion is exactly the same, except the cases are different, and instead of increasing ranks, we're generally decreasing ranks. We're doing demotions instead of promotion. And in all instances of balanced trees that I'm aware of, there are more cases in deletions than in insertions. Generally 4 versus 3 or 8 versus 6 if you include symmetries. Now with AVL trees, it's interesting to note that the original paper, the 4-page paper, Adelson, Velsky, and Landis, only talked about insertion. There was a U.S. aerospace engineer who wrote a multi-page technical report describing how to do deletion in AVL trees, which was more complicated than necessary. But again, it indicates that some people were having trouble with deletion in these data structures. With AVL trees, it's the rotation cases that are non-terminating in deletion. So when you do a deletion, you may have to do logarithmically many rotations rather than just a few. If we relax the definition of balance to allow two nodes, as I have suggested, allow all rank differences to be 1 or 2, giving us these rank balanced trees, we get 8 cases for deletion, but we make the rotation cases terminal. And there are at most 2 rotations per deletion, just as per insertion, which is a very nice property. And here are the cases. There actually are 2 non-terminal cases. There's a case where you have to demote a single node, and there's a case where you have to demote 2 nodes. And again, there's a single rotation case and a double rotation case. Okay. The tree height in these rank balanced trees is at most 2 log n, which is the same as red-black trees. But you can say more for these trees. In a way, they represent a nice compromise between red-black trees, or a nice hybrid of red-black trees and AVL trees. If you just look at the number of insertions and use that as your figure of merit, if you build a tree starting from nothing and do m insertions and arbitrary intermixed deletions, then it turns out that the maximum height is the same as the height bound of an AVL tree built by m insertions and no deletions. So the maximum height is at most the minimum of 2 log n and log base phi of n. Now this is 1.44 binary log of m. Now the right-hand bound is a lot smaller than the left-hand bound unless the number of insertions becomes very large compared to the number of elements currently in the tree. For example, if you delete only half the items in the tree, m is 2n, this is log base phi of n plus a constant. If you delete all but a polynomial, small polynomial fraction of the number of nodes, you still get constant log n, the number of items in the tree. So except in extreme cases, the right-hand bound is the one that is the tight bound. Another interesting thing about AVL trees and these rank balance trees as well is that if you look at that worst case insertion sequence where we insert items in sequential order, you get essentially a perfect tree. You get a tree that has height 1 times log n plus a constant. This is not true of, this is what I just said here. Now, I don't have time to go into the proof of this result, but this latter result, the log base phi of m result, starts getting into, so far everything I've said is kind of undergraduate data structure stuff, although this particular kind of balanced tree is out there in this design space that nobody seems to have looked at until recently, in spite of the fact that many kinds of balanced trees have been around for 50 years. But to actually prove this log base phi of m result, we had to use a rather sophisticated idea, and that's a measurement of balance based on what I'll call an exponential potential function. Essentially, we assign a value to each node, which is exponential in its rank somehow. Potential goes into the system at the bottom, one at a time. The total potential in the tree is bounded by the total number of insertions. When the tree height grows, because of the definition of the potential function, there's an exponential amount of potential that leaves the system. That means the tree height can't grow very often. That guarantees this bound. Many technical details, but not too many. Okay. Now here's another thing that you can prove by a more sophisticated kind of analysis. A very simple analysis shows that if you add up the total number of rebalancing steps over an arbitrary sequence of insertions and deletions, it's not logarithmic times the number of insertions and deletions, it's only constant times the number of insertions and deletions. So not only are there at most 2 rotations per insertion or deletion, but if you sum the number of promotions and demotions, rank changes of nodes over the entire sequence, it's linear in the number of insertions and deletions. That means that in a rather weak sense, the action is happening at the bottom of the tree. In order to propagate up to rank k, you have to do k steps. Well, this can only happen 1 over k fraction of the number of updates. This, we can prove a much stronger result. We can show that the number of updates that propagate up to rank k is exponentially infrequent in k. Okay, this means, this is for rank balanced trees. You can prove a similar result for red-black trees. It's not true of the original AVL trees. In fact, not even this result is true of AVL trees because they're a little bit too tightly constrained in the balance condition. All right, this result again we prove with this much more sophisticated analysis based upon exponential potential functions. This is sort of the key new idea. This idea was used by Huddleston and Melhorn to analyze B trees, which are the multi-way balanced search trees used in most modern database systems. And we managed to simplify it and apply it in binary trees. All right, now, as I mentioned, this is good for a multi-threaded or concurrent environment because it means that almost all the time, all the update stuff is happening at the bottom of the tree. Now, let's come back to our original question, deletion in balanced search trees. It's problematic, first of all, because we may need to do this swapping. We get more cases. The cases require more context to determine which case applies, which reduces synchronization. If we look in particular at the double rotation case on deletion, we have to look at this context, which is a node and most of its grandchildren. That's no fun. So, we know there are theoretical solutions, but what has happened in practice? Well, there are many textbooks that don't in fact discuss rebalancing on deletion. They'll say, here's the balance condition, here's how you do insertion. Deletion, go do this exercise. Okay, here's something more interesting. In several well-known popular database systems that use B trees, they don't in fact do rebalancing on deletion. Now a B tree is a multi-way search tree. It's designed to be used in external memory where you have pages of memory that can hold a certain amount of stuff, and you make each page a node, so a node can hold pointers to a certain number of children and a certain number of keys to do the test for the search. When you try to stuff something into a node that doesn't have space for it, you have to split the node in two. That split requires putting a new item in the parent, and the parent may split as well. Okay, so instead of rotations, it's a splitting process on insertion to do the rebalancing. On deletion, the original definition of B trees is the inverse of splitting, essentially. If a node becomes under full, which means less than half full, you either borrow something from a sibling to fill it up again, or you take two nodes and fuse them together. Splitting you have to do because you've only got fixed storage space, but this refilling on deletion or fusing, you don't really have to do. You can leave nodes as under full. And it turns out that people have built databases that don't do the standard rebalancing in B trees on deletion. And they work well in practice, and people have done empirical studies and also some empirical analysis to suggest that this is okay. Now, this comes back to this unnamed database provider, which decided it was going to implement a balanced binary tree data structure. They chose red-black trees. Either they read the wrong textbook, or they looked at these results on multi-way trees, and they decided they didn't have to rebalance on deletion. Well, it turns out that binary trees are not the same as multi-way trees, and this disaster ensued. One can construct examples where what they did, if you do a bad sequence of insertions and deletions, you can grow trees that have long paths in them. And not only is this theoretically possible, it happened in practice in this example. All right. So that leaves us with the question, what can we say? Why does it work in multi-way trees? Why does it not work in binary trees? Can we make it work in binary trees? That is this idea of avoiding rebalancing on deletion. All right. Now, the database people, as I said, had no worst case analysis. They probably assumed that you can construct worst case examples, but in fact, in the multi-way data structure, the B-tree data structure, the way they did it, in fact has good properties, and you can take their ideas and apply them to binary trees. But in order to understand what's going on, you need to use these exponential potential functions, it seems. So you need sophisticated theory to provide the answer to this question. All right. So this exploration of the state space led us to this idea that I mentioned before of relaxed AVL trees, ravel trees. The height is logarithmic in the number of insertions. Insertion and deletion take constant time in the amortized sense, which means that the total number of steps in a long sequence of insertions and deletions is constant per insertion and deletion. Rebalancing affects nodes exponentially infrequently in the height, just as in the rank balance trees that I described before. Insertion is essentially the same as what happens in AVL trees, and deletion is the same as what happens in unbalanced trees, with one crucial idea thrown in. We maintain ranks, not rank differences. So we preserve the ranks of nodes when we do deletions. And this is the crucial idea that makes this all work. This means, as a minor drawback, that instead of storing one bit of balance information per node, we have to store a few bits, log in the number of insertions. But that's a minor drawback given the benefits that we get. All right, so we allow arbitrary trees. Any tree is a ravel tree because you can always take a tree and give it its nodes ranks to make all the rank differences positive. But the properties come from the way the operations are done on the tree. So we always assume we start out with an empty tree and we build it by a sequence of insertions and deletions done according to the insertion and deletion algorithms. Here's an example. Ravel is a pun. So ravel, you think of twisting together, but it turns out that one definition of ravel is actually unravel or disentangle, to undo the intricacies of. This data structure disentangles the intricacies of insertion and deletion. And not only can we prove nice properties of this thing, but the constant factors are much better and the analysis is much simpler because deletions are trivial. And we don't have to worry about the interplay between insertions and deletions. As I said, insertion works exactly the same as in AVL trees, except that these 2's in here are all essentially greater than or equal to 2. We can have arbitrarily large rank differences in here. And I think that should be a greater than or equal to 2 if I'm not mistaken. There's one bug in this slide. And deletion is exactly the same as in the unbalanced case. except that nodes retain their ranks, not their rank differences. So this broken database that I mentioned before took the idea of red-black trees and tried to do the same thing, except with just one balanced bit per node, which was essentially retaining the rank differences, not the ranks, which means that if you delete a unary node, the effect is to move the entire subtree up. And this can create situations in which things can become badly balanced, and indeed really badly balanced on natural insertion-deletion sequences. That's just an example. Okay, so if we do M insertions intermixed with arbitrary deletions, we get the same height bound as for AVL trees with M insertions and no deletions, and the same as these rank balanced trees with arbitrary intermixed deletions. So if the number of insertions, if the number of deletions become very, very large, if we delete almost everything, then this is not logarithmic necessarily in the number of items currently in the tree. But in many reasonable scenarios, this is a perfectly good bound. If we want the tighter bound where the height is logarithmic in the actual number of items in the tree, we can run a background process that gradually rebuilds the tree, essentially by doing reinsertions of items. We've converted deletion into a delayed reinsertion process. Or if we're willing to shut the system down, we can rebuild the whole tree periodically. But it can be very, very periodically. This can be a very rare event. The background rebuilding process can be very slow. All right. And we get the same kind of result we had before, that rebalancing at a given rank or height is exponentially infrequent in the height, and we actually get a better constant factor than with these other data structures. This is the golden ratio as the base of the exponent, it's the golden ratio. Okay, I think I will stop at this point and I'll be happy to answer questions. Now there's a completely different approach that I didn't talk about to balance trees, and that's the self-adjusting tree, which I'm going to have to figure out. Where's escape on this, Sid? Top left. Thank you. Here's a self-adjusting search tree, which is the other possibility of this kind of data structure. Thank you. Well, let me just mention one quote of Alan Turing that I thought was very nice and fits in here. He said, "We can only see a short distance ahead, but we can see plenty there that needs to be done." And even in the simplest data structures and algorithms, the design space is so rich, I'm sure we haven't found the optimum solutions yet. So there's plenty of work for all of us and all of our students to do going forward. Okay, questions?
You mentioned textbooks. So my question is, what variety of balanced search trees you would include nowadays in an undergraduate textbook? AVL tree, red-black trees, or your new trees?
Well, I teach an undergraduate course, and I've got a set of notes. They're actually online. You can find them. I'm doing some combination of these rank balanced trees and the more relaxed trees, the ravel trees. So that's my answer. I'm hoping that these data structures, even though they're new, they have better properties than existing ones, and I think they deserve to be taught.
So a search tree orders one-dimensional ordered list. Suppose we had a two-dimensional thing that we wanted to order. What would the data structure?
Or a multidimensional, storing multidimensional data is a really interesting problem. There's been a huge amount of work done on it. Generally speaking, depending upon exactly how you define the problem. You pay a log factor for each extra dimension. Although there are situations, certain kinds of query problems, generally what you're interested in is range queries, where you put bounds, upper and lower bounds in all dimensions, and then you want to return everything inside the rectangle. So roughly you pay a log factor per dimension. So in 2 dimensions, the search time would be log squared, log cubed, and so on. Except that you can solve 1.5 dimensional range query problems in logarithmic time. There's a beautiful data structure called the priority search tree invented by Ed McCreight that combines a search tree with extra information, heap-ordered information. But this is only the most basic kind of data structure, and there's a vast literature on addressing this question.
So I have 2 related questions. One, you didn't mention it, but I assume there's a role when you start the tree up for randomization so that you avoid that worst case scenario that you showed up. But that's just the way it gets started. The real question I have has to do with whether anyone has analyzed trees that allow you to put in, let's say, a special node. All your nodes are sort of comparing left and right to see which way to go. But suppose you had a special node that you could put in down at the leaves or a few up that says whenever you come to this one, check both of them down to see something about which way to go, and then go down from there. Now, I don't know exactly what you'd put in, but has anybody done an analysis of the insertion of random kind of nodes that would let you make that kind of test?
That's an interesting question, and I don't really have a good answer for you. Game trees have this and/or property, where certain nodes are or nodes and certain nodes are and nodes. And one kind of node you want to search down only one direction, and the other kind of nodes you want to search down both directions simultaneously. It's a little different domain than the kind of thing that I'm talking about, but there may also be instances of it. Well, if you want to do range queries, you can think about this kind of thing. That's kind of a half-baked answer to your question. With regard to randomization, it's interesting. There are various kinds of randomized search trees, and the nicest one involve assigning a random value to each item in the tree and then using that to determine the balance. And the items are heap ordered with respect to the random choices and symmetric ordered with respect to the keys, and then you get essentially the behavior of you turn the worst case into average case by randomization. Another thing that you get is history independence. With these classical kinds of balanced search trees, the actual tree structure depends upon the sequence of insertions and deletions, not just on the set of items in the tree. But these randomized search trees, the snapshot, the current structure, depends only on the particular set of items that are sitting in the tree, not the sequence of insertions and deletions. And people have applications for this idea. It's a nice property. It may be related to this thing that Shafi was talking about concerning unique outputs of randomized algorithms. I don't know. Thank you.